Yeah. Am I recording here? Yeah, I'm recording here, but I didn't record my local copy. Do I have my enough space? Where is my space? Yeah, that's good enough. That should be good enough. Yeah. Okay, so it will be approximately as follows. So the midterm exam will be 25%, final is 35%. Your homeworks for the undergraduate students, it will be 40%. For the graduate students, it will be 30%. But graduate students are supposed to implement some papers and present them. Okay, that will be 10% of their 10% of their grades, and this is compulsory for the grads. Okay, that means that if you don't do this, you cannot pass this course. You should do this part because that's important for the graduate students. Okay, good. So that will be the grading, and for the homework, I expect you submit at least 70% of the homeworks. Okay, so there will be 4 to 5 homeworks, and you are supposed to do, of course, all of them. If you missed 1 or 2 of them, maybe that will be okay as long as you are not above this threshold. Okay? You are allowed to be late on the due dates, but for each day late, you will lose 10% of your maximum grade, and you can be at most 5 days late. That will be it. Okay, but if there are any situation that prevents you from turning your homework late, or time, some personal cases, and then just send me an email and we will try to figure something out. Exams, okay, it will be, well, no, this is not online. It will be midterm exam. It is all on-site, face-to-face midterm exam, 8th week of the semester. And again, on-site final exam, second week of the finals period. Okay, so that will be it. Maybe I should fix these. So, and I should, while I am fixing this, because this is a new development actually. Okay, so that's it, and let me put this compulsory here. Yep. Okay, this one on site, and this is the attendance. Okay, attendance is required, and attendance will be taken regularly. Okay, and due to COVID-19 conditions, only 30 people said that, because I was assuming that I was going to get the 207, which is a smaller classroom. Now we have this classroom. This is going to go away. Okay, I require 14 in class attendance. Okay. So, well, the university regulations say that if you miss more than 30% of the classes, you will get a grade of NA, and we will follow that one. So this is not a hybrid class anymore. This is a face-to-face class. Of course, I am going to record all the lectures, and I am going to make them available on YouTube. Also, it will be recorded on Teams. You can watch them later, but you are supposed to be in class. So that will be that. Okay. So Those are the attendance stuff, and this is the homework submission and announcements. Okay, everything will be through the Teams pages, so you are supposed to follow the Teams pages. You are not supposed to skip it, and you are supposed to read your emails too. Okay. We are going to use this OpenCV library, Open Computer Vision library, and it will be easiest, I guess, to use the Python interface. So before we start giving you any homeworks, I suggest you download and install stuff and play with it, OpenCV. Okay, we have the honor code, no cheating. Okay, don't use any work from somebody else. Even a single line of code means cheating. So we already know about it. And these are the stuff that we are going to talk about. Okay, this throughout the semester. We are going to do an introduction to computer vision. Then we are going to talk about cameras and some image processing. I know some of you took image processing. That will be, of course, that's why we offered image processing in the first semester and the computer vision on top of it. This is kind of image processing too. And then we are going to talk about segmentation, stereo motion and recognition. So most of the time I am going to spend in stereo motion and recognition, and also the cameras too. So that will be basically it. Let me make this a PDF. Yeah. I am going to replace it, and I am going to make this available for you guys so that, where is my Teams page before I forget? Yeah, here it is. What happened? Yeah. Okay, good. Any questions? Any questions from the online audience? So guys, I am expecting you to come to the class next week, okay? I have only 5 people. Okay, good. Okay, whatever. So if there are no questions, maybe I should start with our introduction chapter. Right? Yeah. So we will talk about today about computer vision, what computer vision is, and what we are trying to achieve with it. Okay. So formally, this is how I define computer vision. Okay. We say that, okay, we have images or image sequences. What's an image? Image is a, okay, is a two-dimensional matrix of data. Okay. Let's say these are my columns. These are my rows. Okay. Each cell of this image, sometimes we call them pixels. Do you know where the name pixel come from? Pixel. It is picture element. Picture element. They kind of shorten it like pixel for some reason. So okay, so it is picture element. So let's say this is 100 rows and 100 columns. Okay, each element has a value. For grayscale images, 0 is the darkest value, 255 is the brightest value. So this is a grayscale image. Okay, so this is a still image. Okay, static image. Just one image. This is a static image. What does that mean? I took this image from a real world scene, and it's a 100 by 100 image. It's an image, okay? Then maybe I can, instead of taking a still image like that, maybe I can take many images, okay, like that. This is by time, so each one is a 100 by 100 image in this case, okay? So this makes a video. Okay, video is just images one after the other one. Okay, we call this a video. So this definition says that images or image sequences. So you take images or image sequences from the real world and you extract descriptions of the real world objects. Okay, you extract the descriptions of the real world objects. For example, I took an image of a, for example, I took an image of a car. Let's say this is a car. Okay, so I took this car picture, and I am, for example, in this case, I am measuring the length of it to see if this car would fit in my garage or something like that. Okay, or I have another image. I have many people in this image. Small people, large people, people near to me, people far away from me, and I'm counting the number of people. The result is 3 out of this case. So I am extracting the properties of the real world objects, descriptions of the real world objects. So computer vision does that, okay? Computer vision does all these tasks, okay? Performs all these tasks from images or image sequences. What kind of things? Geometric stuff, for example, the length of a car, okay? Or the position of the car, or the other objects, okay? It could be geometric extractions or sometimes dynamic. For example, how do I do the dynamic? Let's say this is a video of a car moving on a highway, on a motorway, and I am measuring the speed of that car from this video. So in this case, the extraction is dynamic. It is the velocity of the object, velocities of the object. Okay, so this is a dynamic extraction of the real world object properties. So you always talk about extracting the properties, descriptions of the real world objects. Okay, so why I keep saying the same thing over and over, the real world objects and etc. We will come to that, because some people might say that, well, I mean, image processing, the area of image processing is doing the same thing too. It works on images or image sequences, but we will talk about it. So there is an important distinction between them. Okay, so before we continue and compare this computer vision with other fields, let's talk about what kind of things we can do with computer vision. Okay, we have the medical applications, we have augmented reality, object tracking. Does anybody know what this shape estimation, shape pose estimation is? Shape pose estimation. What is pose? Are they talking?
For instance, our body pose estimation. I understand the keywords eklem.
Joint.
Joint.
Yeah, okay. You could say that your joint positions and joint angles could be like a pose. Human body as a pose is a difficult thing. Let's talk about pose of, for example, a car again. Okay, I mean, you could say that there are basically 3 parameters of a pose. Where is your X, Y, Z position? Okay, in the real world, that's one thing. What are your rotations around theta and gamma, the rotations around each axis, and what is your scaling, okay? So that will be a pose parameter set for a car, for a rigid object. So finding it is where it is in the real world. How, for example, this is an object. If I do this, I am changing just the orientation of it. If I move it around, I am changing its XYZ. With respect to you, if I move it towards you, its scale is getting bigger and bigger, and now it is getting smaller. So finding the poses of rigid objects like this one doesn't deform, is difficult, and finding the objects like human body is even more difficult, because I can do this deformation. I can deform my hand and my arms and etc. Okay, so shape pose estimation is a very important area in computer. We are talk about it. Industrial inspection is important too. Remember the car estimation of the car length? Well, I mean, that might be a stupid example, but estimation of the length of, for example, I have a part like this, a industrial part out of metal. There's supposed to be a circular hole in there, a rectangular hole, an ellipse like hole like that. Okay, I like to know if my holes are centered perfectly, ellipse is perfect, and I like to know if their width and the heights are perfect. Okay, if I can find those, and if I can say that this is a good part, I can sell it, and I am doing industrial inspection. Okay, or I can do the object recognition. For example, I gave you a picture. What kind of things do I have in this picture? It is important. Why? Because think about autonomous cars. If the car is moving along a road, and if it is trying to recognize all the objects on that road, well, I mean, there's supposed to be lots of trees on the sidewalk, near the sidewalk, that's okay. And there's supposed to be lots of pedestrians on the sidewalk, that's okay too. But if I see a pedestrian on the road on which I am traveling, then that's a problem, right? So recognizing the objects and maybe doing the pose estimation is something important for an autonomous car. Okay. So let's look at some of these. For example, I'm going to skip this one. Well, this was a very interesting application. It's kind of faded away, but just to tell you what kind of things we are interested in. This is called Photosynth. Maybe a similar stuff is being done. This guy, see this guy? This guy is the author of the book. Okay. I think this is from 2010s, something like 10 years ago. They do this. From Instagram, from Facebook, from wherever the images are available, they collect the images of people who took their photographs of the famous places. For example, if you go to Sultanahmet Square, okay, you see that lots of tourists are taking pictures. If I download all those pictures from the web, if I put them together, maybe I can do a 3D reconstruction of Sultanahmet Square out of those pictures. Okay, so this is what it was doing, and they were saying that I can reconstruct Rome, central part of Rome, or Vatican, or Paris, and those kind of famous places, the central parts of them. Okay, so this is called photosynth application. So what are we extracting in this case? Okay, we are extracting the position of the camera itself. We say that this picture is taken at this position, XYZ position, and my orientation is that way and that way. Okay, so if you extract all that information, and if I put together all those pictures taken out of those cameras, then I can do the 3D reconstruction of those trees. Very interesting application. And this is a classical problem of optical character recognition. Recognize these letters out of an image. So this is a 4, this is a Y, this is a C. Very important and very popular problem. Well, people have been working on this problem for the last 70 years. As soon as computers started becoming commercial, OCR is important. Why? Because, I mean, if you do the OCR of the printed text, I can get all the text on my computer. I can do natural language processing, or I can read all the text from the books and etc. So it is important. Nowadays, OCR is kind of a solved problem. Okay, we don't do lots of research on OCR, but there is a variation of this. It is called intelligent character recognition, ICR. ICR is the recognition of the handwritten text. Okay, handwritten text. I bet you can't read this word intelligent if you didn't see me write it and if you didn't hear me say it. It is difficult to read human handwriting, but we have lots of human handwriting data, and this problem is important too. For example, it would be very nice to be able to read your exam papers using this ICR technology. Why? Once I read your handwritten exam papers, I can run intelligent algorithms to grade your exams. Okay? Once I grade your exams, that means that doing an exam wouldn't be that difficult thing, and I can make this available for the primary school teachers or the high school teachers. So they can, instead of doing the multiple choice exams, they can do classical exams, question and answer exams, and they will be graded by computers and humans, of course, too. And that would make the things a lot different than now it is, because we keep doing this multiple choice examinations, and everybody knows that they are not very useful in terms of measuring what the people have learned. Okay, so this intelligent character recognition is very important, and we are still working on it. Okay, for the graduate students, if you like to find papers to read and implement something, this is a very good area actually to read papers about intelligent character recognition. By the way, other than the graduate students, our undergraduate students, they can, if they like, they can find these kind of papers. They try to understand those kind of papers and read and implement them. That would be okay too. And I'm going to give them. I'm going to give grades as a bonus, as an extra grade for them, because they don't have to do that. Face detection, again, people have been trying to do face detection, face recognition. What is the difference between detection and recognition?
Detection is knowing that's between these pixels we have a face, but recognition, this face is belong to someone which I seen before.
Exactly. Finding this rectangle and putting it in the right space is the detection. Saying that this is the green person, this is the brown person, and this is the white person is the recognition part. Okay. Face detection has lots of applications, and this was a very difficult problem. And actually, not until 2001, we didn't have any good way of detecting the faces. After that, with the machine learning, we started having lots of successful face detection algorithms, and nowadays, even on the simplest hardware, I can do very reliable face detection. Okay, so these are, again, this is computer vision. What am I extracting? I am extracting the two-dimensional pose of the face. This is computer vision. What am I extracting? I am extracting the characters themselves. Okay, this is computer vision. Why? Because I am extracting the position of the camera in autonomous square. Okay, so we are always extracting some kind of a property, real life property of an object or the thing. Okay, and nowadays our cameras can do smile detection too. Okay, I think nowadays they put animal detection, animal eye detection on the newest cameras, so I can take the. By the way, why do I detect the people's faces on our cameras? Why are we detecting them?
So we can focus on the faces.
Yeah, exactly. So we can focus on them, right? Without focusing, their faces will look blurry. If I focus it, the background will look blurry. Their faces will look crisp and sharp. Okay, and people like their pictures that way. Especially they like the eyes, right? You like to see the eyes in very well focus. Other than the eyes, if the ears are not in focus, then that's fine. I need to see the eyes. Okay, object recognition is of course important. You know this Amazon's new stores, Amazon Go stores. In these stores there are no humans seen in the scene. Okay, these are all customers. You go in this store, Amazon Go store, you take your whatever you want and you get out. That's it. So how does it know? Well, when you go in, okay, this guy, I guess, this guy is doing this with his cell phone. If this is on, then it knows my Bluetooth identification. And they continually, this is full of cameras, the ceiling of this store, okay? It is full of cameras. It knows which products I am looking at, and it knows which product I took, okay? And it knows what I did with it. So as soon as I leave this shop, it just charges me the amount for that item.
And also it knows who I am.
Of course, it knows who you are because you did that with your. I mean, I don't think that they are doing I don't think that they are allowed to do face recognition because face recognition has some legal problems in many countries. You are not supposed to keep biological data without their consent. Okay? If you are going to keep my biological data, such as my fingerprints or my face or my iris pattern, then you need my signature. So it's going to be this. I am going to recognize you from your cell phone.
They maybe use it until you go out from store.
What's that again?
Maybe they use your face until you go out from store, then delete your face.
Well, I mean, you can use my face to track me, to say that this is person A. Person A moved from this position to this position to this position. Yes, that's true, but they cannot associate that face with my identity because that would be using my biological information.
How do they charge us?
What's that?
How do they charge us just knowing the Bluetooth identity?
Well, I mean, when you go in there, you are supposed to register, right? Before you go there, you just register, otherwise they will not take you in. They say that I did not recognize you. Okay? So, we are talking about object recognition here. I mean, whatever I am holding, they are supposed to recognize it. Okay? And they continuously have, I mean, where does the item come from? I mean, if nobody is working in there. Robots, they place all these items in there from the back of the shelves, okay? So it's like a real Amazon store. This is a real picture actually. It works. Amazon Go store. Just look it up on YouTube. There are videos of it. Face recognition, we talked about face detection and recognition, and with the iris detection, iris recognition. Okay, these two persons are the same person. I think this is a 13-year-old girl from Afghanistan, and she's the same person. They didn't know that if she's the same. So they by looking at these two pictures, they identified as the same person. Okay, So that was identified. And login without a password with my face stuff and with my fingers and etc. We already know that. Object recognition. You guys using the Google Lens?
Time to time.
Google Lens work very well with the plants especially. Just point it to a plant and it tells you what it is. And there are very exotic plants available in this campus. One of them is near the E5 connection. It's like an orange, but it's not an orange. It's something else. I don't know. I identified it using Google Lens. It is from Central Africa or something. I don't know how that tree come in this campus, but it is there. So I didn't see that plant anywhere, but only in this campus. So Google Lens object recognition stuff. It will tell you what kind of dog this one is. Okay, Pembroke Welsh Corgi. I don't know. It is much better than. I know only two types of dogs: happy dogs and mad dogs. Special effects. You know this movie, right? I mean, it's a very influential movie in terms of special effects. So these are all the same person, it looks like, but I need to create different face expressions on this one. I need to have the three-dimensional structure of this person. This is how you do that. Okay, so this is a three-dimensional representation of this person's face. Again, extracting the three-dimensional features. This is only geometric. This doesn't have any color information on it. Right? This doesn't have any color information on it. The human skin has very unique color properties. That's another problem. That's a radiometric problem. So what kind of color should I show on this face? It looks like it is very successful in this case too. But before the color, 3D shape is important too. Okay? So this is what I did. So I have to extract the 3D shape properties of this person using computer vision techniques. Okay, you hear about this deep fake. Okay, what you do is you take the color information and the 3D shape information from a person and you synthesize another person exactly with the exact same face expression. Okay, so that would confuse people a lot because this is not a real image. This is not a real expression. You are only stealing this person's face expression and you are putting on this person's expression too. So this is done using computer vision. So getting all that 3D information and producing another. So this deep fake is kind of a combination of computer vision and computer graphics. And we are going to talk about the differences and the similarities between those. Okay, should I continue? Well, sports or the entertainment business on TV has lots of application in terms of computer vision techniques, but it looks like I am out of time. Let me take some break. Okay, 15 minutes of break. Let's be here around 16:37. Is that no? Is that 15? Yeah. 30. Yeah. Okay. 16:37. We will be here. Dersleri bana verdim. Nereye? Ya ben bu geceyi yapıyorum.
Nasılsın Bahçeli'yim?
Nasıl?
Yunus Emre değil mi?
Yok.
Pardon, kusura bakma. Bir kişiyle karıştırdım, kusura bakma.
Bol fotoğrafını çekeyim.
Evet. Toplantının özeti bu.
Erhan Hocam şimdi anlamış, datanızı büyütün demiş.
Dediydi.
Ömer gülüyor, öyle. Çekiyor musun? Abi şey de olabilir aslında ama bilmiyorum. 3D modelingleri falan varsa size yarışmanın verdiği bayağı.
Şey mi? Hiçbir gerek yok. Çünkü kompüter özel gerek yok. Çünkü zaten görüntü geliyorsa insan yazı niye yazar diyor. Sınıf var abi. Bilmek bir bakıp bulabilir de kendisi. İnsan gücüyle.
O an karar verebiliyor görüntüyü gören insanlar. Size
Evet.
şey yapmanıza gerek yok.
Anlamasa da araştırıp bulabilir.
Böyle keyfi
Ama orada şey yok, internet yok yani. Dataset kadar araştırıyor. Bilgisayar da dataset kadar.
Her şey yapabilirsiniz abi. Karar verme mekanizmasını güçlendirici, belli feature'ları mesela 3 tane tip var diyor, tamam mı? Biri parlıyor, öbürü işte nasıl desem, çok sıcak, öbürü de çok soğuk. Bu 3 feature'ın farklı şekilde siz bilim ekibinin göreceği ekranda değiştirseniz belki karar vermeye yardımcı olacak şekilde falan olabilir. Öyle bir şey olabilir. Nasıl biliyorum? Yok çok da şey olmadı. İşte giriş falan mı soracağım? Ser saflık yüz yüze online gibi sınıf büyük yerinde. Onun dışında bir şey yok yani. 25 miktar 30 final 40'ta şey. Bir şey %5 kaçırdım herhalde. 40'ta olmadı işte. Evet.
Hakikaten biraz zorlamış mıydı?
Okay, we have more people. So sports is another application area of computer vision. You know the offside rule in soccer, right? In American football, they have a similar thing. This virtual line is important. So it is usually shown by this marker. Okay. Of course, this yellow line is not drawn on the real field, American football field. This guy is trying to cross over this line, and this line has to be updated after every play. Okay. And you have seen this kind of lines in soccer games, offside lines and that kind of stuff. Or sometimes we do that kind of thing, okay? So this one is, you are okay, what kind of shape is this? What kind of shape is this? It's a circle, right? But it's not a circle, it's an ellipse, right? It's an ellipse, right? So we see an ellipse, but we interpret it as a circle. So when you are drawing this, you don't draw a circle, you draw an ellipse from this viewpoint. Also, these kind of the letters, okay, that's the name of the guy, there's a direction of the movement, and etc. These kind of stuff is very effective in terms of giving the viewer the idea of what's going on, or helping to understand the game, how the game is progressing, and etc. So, and I think I am going to give you 1 or 2 homework assignments about this kind of understanding the camera position, understanding the position of the player, and drawing these kind of circles or the lines on the field so that we can feel that there is a real line of, there is a real circle around that person. Okay? So computer vision is used there a lot. For this one, first you have to find the plane of the field, the football field, the plane of it, 3-dimensional plane, and find the touching positions of these players to that plane, 3-dimensional positions, and then drawing, okay? This circle is bigger than this one. Why? Because this guy is away from me, right? So I know I should know that, okay? This T is larger than this T there, right? See this, right? So why? Because it is closer to me. So how do I make these kind of calculations without knowing the 3D orientation of the plane? Okay, so with the smart cards, typical, see, this is the pose of a car. Okay, so my pose is this. Okay, I get this nice prism, the rectangular prism, and I say that its position is this, its orientation is that way, both this orientation and that orientation, and the how small, how large is its scale. Okay, so this is a rectangular prism for the person, another person, another person. This is basically what an autonomous car sees. Okay, this is basically an autonomous car sees. I don't know what kind of text do I have here. Do you see the, okay? I guess these are the red. Yeah, these are the XYZ positions, the height of it and the distance of it. Right? So I think it is seeing 1, 2, 3, 4, 5. What is red? 1, 2, 3, 4, 5 cars, I guess. Maybe they are 5 cars, maybe persons. I don't know. I mean, it's just giving you all that information for the smart cars or the autonomous cars. And by the way, what are these? It recognizes all these traffic posts, traffic signs. Okay, I found it. This is 411, 411, 21. It's calling it, right? So it recognizes this one, also this one, that one, whatever. So the typical object recognition, pose estimation. Pose estimation is important to know how far this car is away from me. It's important. It has to know its speed too, because if it is stopping, that's one thing. If it is moving, it's another thing, right? So the dynamic features, static features, and the recognition stuff. For the entertainment, for the video gaming, we use computer vision a lot. Okay, Nintendo Wii has a camera and its controllers, infrared camera, it uses a lot to do computer vision stuff. Microsoft Kinect, again, it is using lots of sophisticated computer vision stuff. When you go to space on Mars, whatever you send there, it has to move autonomously because there is a 50-minute delay between Mars and Earth. Whatever you send, it will take 7.5 minutes to go there, and coming back is going to take another 7.5 minutes. So that's going to make a 15-minute travel time, round trip. So you can't say that go left, go right, go left, go right. Okay? You just say that I like you to go this point. Okay, you go there. This guy, this robot, cannot go there without extracting the three-dimensional map of the train there, because it has to know if those rocks are small enough to climb, or if they are large, then maybe I should go around. It has to make its plans by itself. So without using the computer vision, your task would be a lot more difficult in terms of sending these kind of robots to other worlds. Okay. So with the vision space, we do lots of computer vision. Of course, robotics. One example of robotics. Other examples of robotics. If you behave like a living thing in this real world, you have to behave like a living thing. Okay, you have to interact with the other things, other animals, other people, and you have to interact with the objects. You move them around, manipulate them. So you need to do object recognition, you need to do pose estimation, you need to do shape and velocity estimation, etc. These are all tasks for the computer vision. As I said before, medical imaging is another area of computer vision, along with image processing, video loss of medical imaging. This is 3D. I think this is just a slice of a 3D image of a person's head. I think this is an MRI. No, this is a CT image. It looks like a CT image. I am not sure. So there are ways of taking three-dimensional volumetric images of human body. MRI is one of them. Computed tomography is another one. Remember my picture? I took a picture. It is 100 by 100. It's a two-dimensional picture, right? So I have, this is called picture elements. These are picture elements. In the two-dimensional world, it's like that. So when you look at a picture, okay, it's a two-dimensional thing. But if you put the third dimension, I can take these kind of images. Now, this is 100 by 100 by 100, and each of these boxes are three-dimensional small box. And this one is called voxel. Okay? Remember the pixel? This is voxel now. Volume element, right? So, our regular cameras take two-dimensional images. They are just two-dimensional, 100 by 100, that's it. But MRI kind of devices, or CT, computed tomography kind of devices, they can produce image for the internal parts of objects like the human body. Okay? How do they do that? For example, CT works this way. CT works this way. Let's say this is the object that you are looking at. Okay? CT sends radio signals from this side, and it gets the measurement from the other side. Okay? So these X-rays, they can penetrate these kind of objects. They can go through the objects. They can penetrate, and from the other side, if you measure what kind of signal you are getting, you learn some kind of information about that one. And you repeat this from the other side, and you measure it from this way. And you keep doing this from at least a few hundred times from different angles. If you put all that information together, now you can have information about each voxel. Okay? That's how it works. That's how CT works. MRI is kind of different. It uses magnetism instead of the harmful X-rays. MRI is a little bit different. Sometimes we do this kind of stuff with the ultrasound, three-dimensional ultrasound. But that's how it works. So, if I do this, and okay, this is a two-dimensional picture, that's three-dimensional. Because I just, for example, out of this 100 by 100 by 100 image, okay, if I take this slice out, okay, I am taking just this slice out. So this slice is a two-dimensional image, right? And I show you that one. Okay, so this is a two-dimensional image out of three-dimensional value. Okay, it looks like. Okay. So a person's head is doing that. And I can do this for the other slides, or I can do this sliding the other way, axial, coronal, or the sagittal way. They have different names for it. And the doctors, they can inspect these images by looking at two-dimensional images. Or I can do this even better. Okay, I know what is inside this head now. This is a person, real person, who is going to be who is going to be operated on in a few minutes. They are going to cut around somewhere around here, and the doctor, when it looks at this person, there is a projector or the laser pointer pointing to this person's head, and it is drawing where the tumor is actually. Okay, so when you start operating on this person, when you're going to put the incision, okay, you know where the tumor is, and you wanna cut that local region near the tumor area. Usually they have a pretty good idea where to start the incision, but sometimes they can make mistakes and etc. So these kind of stuff are helpful for them. These kind of stuff are helpful for them too. So in this case, what am I extracting? I'm extracting the 3D pose of this head. Okay, that's one thing. Also, I am extracting the position of the tumor from this MRI image, and I register this image with this head, and I say that, well, it has to be somewhere around there. Okay, so three-dimensional computer vision meeting the medical imaging area. Okay, that's another thing. Again, for the last 5-10 years, deep learning made lots of progress. We can do this kind of stuff, captioning. Okay, a person riding a motorcycle on a dirt road, a computer vision is doing this. Okay, computer vision system takes it and it produces this sentence. So for the last 5-10 years, we started having seen these kind of advanced systems that work on images and the language at the same time. Okay, images and language. Either take image, produce language, or take language, produce image, or work on both of them at the same time. Okay, this is called image captioning.
Can you see error given images?
Okay, this one.
Errors.
A dog is jumping to catch a frisbee.
What's frisbee?
Well, there is a dog. Yeah, I don't see any frisbees. Well, erroneous. Well, I mean, this is an old slide. I'm sure these problems are solved. How about this one? A yellow school bus parked in a parking lot. It is yellow. It is a vehicle. Yeah.
Can you see middle?
What?
Can you see left middle?
Red motorcycle parked on the side of a road, kind of reddish. This one is not lying, and yeah. It's funny, a little girl in a pig hat is blowing bubbles. There is a little girl in pig hat, but she's not blowing bubbles. Anyway, so many of these are less than 10 years old, okay, and it looks like we are going to see very exciting developments in the next 5 years, okay, and this is a very fast growing area, and lots of researchers, lots of new people coming into this area, and many new developments. Google is making lots of investment. Facebook is making lots of investment. Amazon is making lots of investment in this area, because the autonomous cars, autonomous space vehicles, space robots, they all have to use the vision. You know what I mean? If you can follow people, if you can guess what they are doing, and if you produce more information out of this extracted information, then that means you are making serious amount of money. So very, very exciting area. It has been that way for the last 30 years. Now the area got even more exciting now. Okay, good. So let's look at this one too. Relations to other fields. Okay. We talked about the image processing. So what is well, many people don't agree with what I'm going to tell you, but I'm going to tell it anyway. So image processing and computer vision, how are they related? With the image processing works on the images or the videos too. But usually with the image processing, the inputs are images and outputs are images too. Okay? For example, you take the left side of this image and you produce the right side. So this is blurry, this is sharp. So you sharpen the image without knowing what's going on inside the image. Is this a person's face? Is this a car image? Is this an image of a building? I don't care, I just make it sharper. Okay? So it doesn't recognize it. Or image compression. I took this image, it used to be 2 gigabytes, now it is 50 kilobytes. Okay? So image in, image out. Image restoration, I made this less noisy. Okay, these are the things that the image processing does. It doesn't extract real world properties of the image underneath. It doesn't say that there is a person in here. It doesn't say, okay, there are 5 people in this picture, etc. Okay, so that's one of the main differences between computer vision and image processing. In image processing, you don't care about the camera. You don't care where the images come from. Okay? Just 2-dimensional or 3-dimensional image. But in computer vision, usually we care about where the images come from. We like to know what kind of camera we have used. Where is the camera located? What kind of lens it is using? Because those kind of things are important to make those measurements. Another one is computer graphics. It is very related to computer vision. Okay? Some people call computer graphics inverse vision. Okay, why? Because in computer graphics you do this. Somebody tells you that, okay, there is a plane, this is a description, right? There is a 3-dimensional plane, and these are its position and pose. There is a ball, and that's the material of the ball and its position and its the size, etc. And then I have 3 light sources. So what do you want? I want you to produce a realistic image of this scene. And I'm producing this image. So I have all these descriptions of the real world objects. And I produce a realistic image out of those descriptions. In computer vision, we do just the opposite. We take the image in and we say that there is a ball at this distance, its diameter is this, and this ball is sitting on a plane such and such, and etc. Okay? So computer vision and computer graphics are kind of the opposites of each other. Okay? So that means that they have nothing to do with each other, not exactly. They use each other a lot. Okay? Remember that deep fake thing? Okay? You need to extract the person's pose and the facial expression so that you can put that facial expression to some other people. And you produce a realistic image of that person. Okay? So computer vision and computer graphics, they collaborate a lot. Computer graphics used to be more popular in 1980s because computer graphics is kind of more how should I say it? It doesn't require that much intelligence. I mean, I did not see many people who say that computer graphics is an artificial intelligence problem. It is not. Okay? Once you know your parameters, okay, it's a matter of finding the correct model and producing your realistic images. But computer vision is an artificial intelligence problem. Why? Because most of the time you don't have a definite certain answer. Okay, you will say that I think there are 15 people in this image with 95% confidence. I mean, if the persons are separated, they are not occluding each other, that would be fine. Maybe you would be 100% sure. But if the persons are one behind each other, then in that case it's going to be different. Okay, so computer graphics and computer vision are definitely related. You have seen, you know pattern recognition. Okay, it usually classification problem. It classifies patterns into finite set of specified classes, 2D data and sometimes 3D data. Photogrammetry is very similar to computer vision, but using the non-contact imaging from the images from the satellites or from the very, very carefully calibrated cameras, it is usually used for drawing maps or extracting maps of the land areas. It is called photogrammetry. Okay? Good. Any questions so far? So I'm going to look at more details of an image now. Okay? That's the definition of an image. Very simple definition. An image is a 2D matrix of numbers. Here you go. Here you go. Here I have, I guess, it looks like this is 15 by 15 image. 15 by 15. 15 rows and 15 columns, a matrix, two-dimensional matrix. Lower the number, darker that position. Okay. Higher the number, brighter that position. So it looks like there are low number there. And if you show these numbers as an intensity, this is what you show. What do you see here? It's an eye, right? It looks like an eye. So each of these small squares, for example, this one is a pixel, this one is a pixel, and this one is a pixel, again this one is a pixel. It looks like, let's look at these two pixels. It looks like those two pixels are, I guess, maybe these two, right? Yeah, 182. So the value of this one is 100, this is 82. Rest of them are kind of dark, like 13s and 15s and etc. Looks like it. So this is a grayscale image. I don't say black and white. Black and white are either 1 or 0, right? 255 or 0. This is a grayscale image. Okay. Its values changes from 0 to 255. And I can represent this image as a two-dimensional matrix. Okay, two-dimensional matrix. So I need to say yes to this guy. Okay, good. So it's a two-dimensional matrix, and I represent it as an intensity. Images, they don't have to represent intensities all the time. Sometimes, okay, you know where I get this image? I get this image from a camera, standard camera, like the camera of this cell phone, okay? But cameras, regular cameras, are not the only sources for your images. Sometimes we have images of position ranges. Let me show you. This is a regular intensity image. I don't know what kind of environment this is. This is like obviously a closed environment. There is an object near here. There are maybe some cabinets. There is another object. I don't know what kind of environment this is. So this is 100 by 100 image, gray level image of a room, closed room, okay, indoor environment. This is an image. It's a range image. The same room, but this time our image pixels, instead of showing the intensity, this one shows the depth, the distance between the camera and the object itself. So it looks like the numbers here are maybe 255, and number here are maybe 20. 20 is less than 255. So that position is close to me, right? That position is not close to me, it is away. So brighter the pixel, away from me. Darker the pixel, close to me, okay? It looks like there is a hole in the middle of this object. and it looks like there is a hole just near here, okay. And I didn't realize it, but it looks like there is an object on the ceiling that is close to me, but I didn't realize it. And maybe this part and this part, you don't see it. Maybe this part and this part, you don't see it either. Maybe this part and this part, okay. Maybe they are equally away from me, right? They are close. They are equally close to me, okay. This is a range image. This is an intensity image. Image is a two-dimensional data or three-dimensional data, but your data element doesn't have to be intensities. Okay, it could be range, depth, or it could be intensity, or sometimes it could be physical properties. What do I mean by this? For example, this is a MRI image, two-dimensional image. What kind of image is this? What part of the body do you think this is? It looks like a knee, right? Everybody knows it. I don't know how many people, how many of you have seen a knee like that. I guess you have seen it from the images, from the pictures, okay? But this is a knee image. I have taken a slice out of a three-dimensional MRI image. And this one is not an intensity or the depth image, okay? This is the physical property. This is the amount of hydrogen atoms on that part of the body. So hydrogen is, of course, it is related with the water, H2O, right? So the more hydrogen you have, it's going to be brighter for that area. So different parts of the body have different levels of hydrogen available, and that's going to show you the structure of it. Okay? So let's say if you have a different region around here like that, of course it's not going to be green, but its intensity will be different. The radiologist says that, okay, there is something suspicious here. I mean, this shouldn't be here because there is no structure like that. So they say that maybe just open this person up and see what's going on. Usually they don't open it. What do? They put a needle in there, okay? They put a needle in there and they take a few pieces of that thing and they analyze it under the microscope and they say that, okay, this is a bad tumor, or, well, it's just a piece of fat, okay? So for that one, they need to know where the tumor is, and they need to know if there is a tumor or not, okay? But again, this is a physical property. It is not intensity. It is not range. It is just the amount of hydrogen that you contain in that specific part of the body, okay? Again, this is for me an image. This is image, and this is image. Depth image, intensity image, physical property image. And we are going to see different kinds of images. For example, the disparity image about the stereo, and you will see. Okay? So, image means two- or three-dimensional data. The meaning of each element of that data changes from image type to image type. So what kind of camera do you think this one is produced from? This is my cell phone camera. How about this one?
There are things like laser method. They calculate the distance between object and various. Maybe it's something like this.
Radar kind of stuff you have to really. I mean, maybe sometimes it is sometimes it is sound based. Okay. They call those kind of cameras sound based cameras or sonar cameras, okay, sound-based stuff. Sometimes it is based on electromagnetic waves. Sometimes it is laser-based. In the laser-based one, it works that way. They send a laser beam, okay, then wait until the laser beam hits some place and comes back, reflection, and they measure the amount of time of the flight. It's called time of flight camera, okay. So they do this millions of times a second. They send a laser, they wait, and they They measure the time difference, and they bounce this laser beam on all the places in this room, and they how they measured it. LIDAR, I'm sure you heard it. LIDAR, okay. LIDAR. It works that way. On many cars, autonomous cars, they have their LIDARs, laser-based radar. Okay, it works that way. Some autonomous cars use the RGB images. Some of them use sonar. Some of them use LIDAR. So technology changes. All of them, they try to do it for measuring the depth. It is important to know how far away the car in front of you, right? If it is too close, and if it is getting even closer, then maybe you should brake. Okay? So, good. So we looked at those images, and let's look at this image formation process now. That's going to be our main thing actually, okay? So basically, we will many times, we will try to talk about intensity images, especially at the beginning of the semester. But when the time comes, we will talk about these range images, depth images, physical property images when the time comes. But for now, let's talk about these intensity images, and let's see how those intensity images are formed, okay? So what happens when I take a picture of some place using this camera, okay? There are three aspects of it, at least with respect to what we are interested in, okay? There is an image geometry. There is a geometry part, which is the most important part. Geometry means this: if I know that projector is at position XYZ in the real world, if I take the picture of that projector like that, and I'm going to produce a two-dimensional image, right? On what part of my image I'm going to see the projector? What column of the image and what row of the image, X and Y positions? That's the image geometry. This photometric parameters of the image is this. Okay, I know that projector, I know that it is made of plastic, I know its color, but on my image, under the given circumstances, what kind of intensity level it is going to produce, okay? So the photometric parameters are responsible for the intensity levels. This image geometry is responsible for where it is going to form that intensity level. Quantization and sampling, well, I mean, the real world is a continuous world. We don't have any discretization of the real world inside the world, but our world, computer world, digital world, as the name implies, it is all discrete, right? I have to separate, I have to name my columns and rows on my images. I don't have a continuous image, right? So this quantization and sampling talks about it, okay? There is a first row, second row, third row. There is no two and a second row, okay? I know that. There is the intensity level, 100 and 100, 102 intensity levels, but we don't have an intensity level of 125, okay, 100.25. So one of them is sampling, the other one is quantization, and we will talk about them because these are unavoidable problems of digital images. Mostly we will talk about this image geometry. Let's talk about that one. Projection is going to be our main tool about dealing with this geometry. What do you see in this image? This is a real image, by the way. It's not fake. It's a real image. What does that guy do?
He stands like he is standing on the image, but he is only far away.
Is that a very small person? What kind of image is it? Well, this is the kind of image. If I take this image from another view, this is what they did. They painted the sidewalk that way so that it gives me the illusion of seeing a sphere, and if I put a man like that on top of it, okay, but this illusion only happens from this point, okay. So what's going on? Our world is a three-dimensional world, okay, but images are two-dimensional. So when I take an image of the real world scenes, okay, I produce a two-dimensional image. So that means what? I lost a dimension. So I lost lots of information actually, right? I mean, going from three-dimensional world to two-dimensional world is called projection, by the way. You are projecting a three-dimensional world, okay, into a two-dimensional world, 3D to 2D, and you are losing lots of information. That's the difficulty about computer vision. Computer vision tries to figure out the details or the properties of the three-dimensional world using two-dimensional data. That's the problem. Most of the time, as human beings, we are okay with it. I can take care of myself. I can walk without falling most of the time. I can manipulate objects. I can take this and I can put it on there, and I know that it's going to stay there, even though my eyes see it in two dimensions. Two-dimension and two-dimension. One would say that, okay, you are seeing it from two different directions, and that's going to give you a three-dimensional sensation. Yeah, that's true. But again, I can do the same thing using one eye, right? It's going to be a little bit more difficult, but it's going to be just one eye, right? So that's called the projection, and that's one of our problems. We lose lots of data when we take images of the objects from the 3D world. But even though it's a tough problem, humans can deal with it, animals can deal with it. So why shouldn't we? That's what we're going to do with the computer vision. That's the projection. Okay. So basically, we will use that idea, projection, and we are going to do this. If this is my object in the real world, and if I'm trying to take the image of this object on a film, okay, on an image plane, so what would be the relationship between this object and the image itself? Okay, but I think I am over my time now. I will stop at this point and I will continue next week from this point on. Are there any questions? So online people, they never said anything. Maybe they did. I did not hear it. Did they say anything? They say yes, we do. Oh, that was a long time ago.
When we asked for, are you hearing me?
Yeah, okay. Okay, people, next week we are meeting in class. That was more slides. Oh, okay, thank you, Ikram. Unfortunately, I cannot read these chat messages. Please, if you have any questions, just raise your voice, use your microphone, and ask me questions or ask me things. Next week, I will meet you in the classroom, and I may not. Well, I'm definitely record the videos, but I mean, depending on the case and depending on the situation, I may not stream the lecture because I am expecting in the class. Okay, if there are no questions, then I will see you next week. Arkadaşlar herkes imzaladı mı bunu? İmzalamış herhalde. Güzel.
Hocam nasılsınız?
Şükür vallahi iyi, sana ne var?
Hamdolsun hocam, ben değilim. Hocam çarşamba falan müsaitseniz bitirmeye ilgili toplantı yapabilir miyiz? Ben paper'ı okudum, gözden geçirdim.
Anladın mı bir şey?
Yani hocam bir fikir sahibi oldum ama yani
Tamam, güzel bir şeyler, yani en azından ne yapmaya çalıştığını